Since Professor Dera is here, we continue. Okay, in this session, the first speaker is Professor PÁL BURAI from University of Debrecen, Hungary. He talked about optimality conditions involving generalized convexity and convex analysis. Professor?
Okay. Thank you, Mr. Chairman. At first, I would like to thank the possibility to the organizers to give a talk here, so thank you very much. The title of my talk, Optimality Conditions Involving Generalized Convexity and Convex Analysis. Here, mainly I will talk about optimality conditions of unconstrained problems and objective function mainly defined on a real Banach space and it has real values. So let me start with the outline of my talk. There will be two main parts. In the first part, I will talk about optimality conditions involving convex analysis tools. And in the second part, which contains three subsections, I will talk about local global minimum property of mainly local global minimum property of functions. Local global minimum property means that classes of functions which poses the following property. Every local minimizer of the member of this class also a global minimum. So this is the so-called local global minimum property, which is very important in optimization. So at first, in the second part, I will introduce a generalized convexity notion, which, according to my best knowledge, used at first by Ortega and Reinbold in 1970. This is called connectedness of, or quasi-connectedness of functions. This concept introduced in their book entitled Iterative Solution of Nonlinear Equations in Several Variables. After that, I introduce a modified or a generalized directional differentiability notion which fits better to this concept of convexity. And at last, I will show an application from calculus of variations. So let's start some basic notation from convex analysis, which is known for everybody, I guess, here. X is a real Banach space. X star denotes its dual space. That is to say, all the continuous linear functionals defined on X. And this brackets denotes the canonical pairing between these spaces. And here is the polar and the bipolar of a given function, or fancial conjugate, or the conjugate of the function, which defined with this formula. This is the first conjugate, and the second one defined this formula. I think these are known. And the first theorem gives a necessary and sufficient condition on global optimality. The finite dimensional version of this theorem due to Iriart-Urruty. Here is a Banach space version. So let X be a Banach space and F defined on this space with real values. And assume that F is Gatto differentiable and continuous at a point, say X bar. Then this point is a global minimum of F if and only if X bar is a stationary point. This means that the Gatto derivative is equal to 0 at this point, and F coincides with this bipolar at this point. But what is the role of this theorem? It is well known that if we have a really nonlinear optimization problem, I mean that where the objective function is non-convex, then usually the second order conditions ensures only local optimality instead of global optimality. But if we know something more about the function, I mean more about its global behavior instead of local behavior, say convexity, then This ensures that the local minimum is also global. But here, we use only Gatto differentiability. So this is a first order local approximation of the function and a convex analysis tool. And together, these two ensures global optimality. It is also clear if we assume that this is easy corollary of this theorem. If you assume that the function is Frechet at a point, then this implies Gatto and continuity at the same point, so we get a similar theorem. But here we cannot weaken the assumptions. So both Gatto and continuity are essential here, because without these assumptions, the theorem is not true. And these regularity assumptions, together with the assumption that the function coincides with its bipolar, also essential. For example, if we have a very easy example in R, then it is easy to see that this function coincides with the second dual at the point 3/2. And this denotes the subdifferential in the sense of Clark. So it is more general than the subdifferential. And the 0 is in this subdifferential, but it is not true that this is a global minimum of this function. Some proposition in connection with this. If x is a stationary point, so again, this means that the Gatto derivative is equal to 0 at this point, and it coincides with its bipolar, then this implies the regularity of the B-dual, namely the second dual of the function is also Gatto differentiable at the same point, and the Gatto derivative is equal to 0 at this point. And it's also this is almost trivial that actually it is trivial that global optimality, so a necessary condition on global optimality that the function is equal to its B-dual at the point. This is not so important. So after this, it is well motivated now to characterize such points where the B-dual is equal to the original function. It is known that if a function is convex, then it's a nice convex function, then the function is equal to its B-dual. But if it is non-convex, then being equal to its B-dual means that this equality, and it's nothing else, but there is, for all positive epsilon, there exists a non-empty subset of the dual space, and this subset depends on epsilon, such that this inequality fulfilled for every x from X and from every X star from this subset of the dual space. This is nothing else but the approximate subdifferential, actually. This set was introduced by Bronsted and Rockefeller in 1966. And after this calculation, it is clear that if a function equals to its B-dual at a point, then it is also true that all the subdifferentials are all the approximate subdifferentials are non-empty, because in this case also the subdifferential is non-empty, and the approximate subdifferential is a monotone increasing function of epsilon. So if epsilon is equal to 0 and it is non-empty, then this means all the other approximate subdifferentials are non-empty. But the opposite is very far from being trivial. In 1966, Bronsted and Rockefeller proved that the approximate subdifferential approximates well the subdifferential in some sense. But here, f is not necessarily convex, so the sufficiency part is interesting or not trivial. Namely, if a function is locally Lipschitz at a point, then f is equal to its bidual at the same point if and only if, for all positive epsilon, the corresponding approximate subdifferential of f at this point in question is not empty for every positive epsilon. This positiveness is very important here. So this is why it is not trivial. The sufficiency part is not easy. The other is trivial even if we don't assume local Lipschitzness of the function in the point in question, at the point in question. The other guys try to characterize such points where the function not equal to its bidual. We introduced this set for this characterization. This set unfortunately depends on two parameters, three, but the main parameters are here. So one of the member of the dual space and an epsilon from an epsilon. So this set is a subset of the space, not the dual space. The subdifferential is the subset of the dual space, but this is a subset of the space. And this proposition says if a function is not equal to its bipolar at a point x bar, then this set is non-empty for every x star from the dual space. And conversely, if there exists a positive epsilon such that this set is non-empty for every x star from the dual space, then the function is not equal to its bipolar at this point. So this is not a characterization, but almost a characterization. Okay, this was the first part of my talk, and let's turn to the generalized convexity. So as I mentioned, this concept was introduced by Ortega and Reinbold in 1970. Here, they introduced this concept in Rn, so in finite dimension, but later Avrier and Sang generalized these definitions and they used topological spaces. So let X be a topological space and D is a subset of this space, and F is defined on this space with on this set with real values. And this function is called quasi-connected and connected on this set on D. If for all x bar and x from D there exists a continuous function, which called the path joining x bar and x, defined on the interval 0, 1, with the values from D, such that gamma and f fulfills the following conditions. The first one, for all t from the interval 0, 1, gamma t is in D. It is nothing else, but if we consider or take into account gamma as a generalized section, then this means that the sections in this sense are in the set D. So the first requirement means that D is convex with respect to these gammas. So one can use the terminology D is convex with respect to this family of generalized sections. The second means that gamma connects x bar and x. So if somebody change gamma into the normal section 1 minus t times x bar plus t times x, we get the normal or usual concepts of convexity. And the third one is the defining inequality of convexity. So f of gamma t less than or equal to 1 minus t times f of x bar plus t times f of x, or here is the quasi-connectedness. Here is the inequality which defines the quasi-connectedness. Let's see an example. Let's just consider this Rosenbrock-like function. Like means that in the original definition of Rosenbrock function, there is a 100 multiplier here. This function is quite popular and well known in numerical optimization. The other name of this function is banana-shaped valley function, because there is a curved, very deep and narrow valley at the bottom of the graph. And why it is so popular? Because if we have a numerical method based on, for example, steepest descent directions, and if we go down, at the bottom somewhere at the valley, then we have two choices: go up or go down, but to go down with very, very, very small steps, because the bottom of the valley is very, very narrow. So this is why it is so popular in numerical optimization as a test function. And it's clear that this is not convex. Also, it is easy to verify that it has only one global minimum at the point 1, 1. And the global minimum is equal to 0 because this is always greater than or equal to 0. And that 1, 1 is equal to 0. And if the point is different from 1, 1, this is greater than 0. So it has a unique global minimum. It is not convex. But if we define the gammas in this way, then this function is convex with respect to this family. We will use this example later. So I have 10 minutes. I have 10 minutes. Okay. Then I skip these, and let's carry on with this. Okay. So something about this generalized convexity notion. If X and Y are topological spaces and we have a homomorphism between these spaces, then if we have a quasi-connected or strictly quasi-connected, connected, strictly connected, and so on, strict means that we have a strict inequality when X is not equal to Y. So if we have such kind of function and we perturb the underlying space Y, then the composite function will be also quasi-connected, connected, and so on. So this means that under a nice perturbation, this property is preserved. This is very important in optimization point of view, and it's very important to know that if a function is convex, then this is not true. This is clear if we perturb the space with the homomorphism, and we take this composite function, this is not, it won't be convex in general, but it is true it is convex, then the composite function will be connected. And, by this class, or these classes are important in optimization point of view. This is verified by the theorem of Avriel and Zhang. If F is connected and so on D, then every local minimizer of F is also a global 1. This means that this class poses the so-called global, local global minimum property. So if we have a second order or first order condition for local optimality, and we know that the function also, we can verify in some way that this function is connected or connected in some sense, so we can find a family of paths, then every local minimizer will be a global 1. And I would like to introduce here a directional differentiability notion which fits better to this convexity notion. Here we change X, so X is a real normed space now, and F is directionally differentiable with respect to a path at X bar, and here gamma connects X bar with X. This is important. If this limit exists. And assume that F has a local minimum at X bar without connectedness assumption, so there is no generalized convexity assumption, and X is not equal to X bar, so this is not so important, and gamma joining X bar with X, and F is directionally differentiable with respect to gamma, then we get this variational like inequality, namely the directional derivative at X bar with respect to gamma is greater than or equal to 0. If we know that the function is connected with respect to gamma, then, and fulfills this inequality for all x, then x is a global minimizer of the function. Let's see an example. Let's consider again the previously mentioned Rosenberg-like function and take the family again. And the straightforward calculation shows that the directional derivative of f at x bar with respect to this gamma is equal to this expression. And if we substitute x bar with 1, 1, and take an arbitrary gamma, we get this is equal to 0. This means that this is a global minimizer. This is known in advance, but this is an academic example of the use of the previous theorem. And at last, let's see an application. This is the most basic problem from the theory of calculus of variation. Here, phi is defined on this product, which is continuous. So this problem makes sense. And the admissible set is equal to the such functions which are defined on A, B, and continuously differentiable, and fulfills these site conditions. This is known that the solution of the Euler-Lagrange equation covers the possible solutions, but it is not true that if a function is a solution of this equation is automatically as a solution of the original problem. But if we know that this phi is convex with respect to its last two variables, then it is true that all the solution of the Euler-Lagrange equation, also the solution of the original problem. But some convexity is needed to ensure this optimality. Let's try to generalize this theorem. Okay, this is a, this is a technical assumption. And if phi is continuously differentiable and fulfills this technical assumption, then every local minimizer of the original variational problem is a global one. It seems to be a little bit artificial of this technical assumption, but I have no time, but I would like to mention that it is possible to verify the simplest case of Friedrichs inequality, which is in the Poincaré inequality family. So it is possible to prove, give a new proof of Friedrichs inequality, of the simplest case of Friedrichs inequality, using this theorem. Okay, and here are the references. This talk mainly based on these two papers from Optimization Letters and the Journal of Optimization Theory and its Applications. And thank you very much for your kind attention.